तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Alright, what I would like to do today is go back a little bit to the Schrodinger equation for a particle moving in 3 dimensions and show you that associated with the probability density, which is mod psi squared, there is also a probability current. And whenever you have a density, you know, in electricity and magnetism for instance, there is a current which is related to the density by the continuity equation del dot J equal to 0. That is true for the charge density and the charge current. Similarly, in fluids, when the fluid is in motion, between the current density and the fluid density there is a continuity equation. So the question you could ask is, if mod psi squared in the position space representation for example has the connotation of a probability density, is there a current associated with it? And the answer is yes, and it goes as follows. So we start by writing Schrodinger's equation IH cross, and now let me write it in the position representation for a particle moving in some potential V of r. So it says delta psi over delta t, and this is a function of r and t. This is equal to the Hamiltonian in the position basis on psi of r and t, and the Hamiltonian is the sum of the kinetic energy plus the potential energy, and in the position basis this is minus h cross squared over 2m del squared psi of r comma t plus some potential V of r which multiplies psi of r comma t. So that is the time dependent Schrodinger equation in the position representation for a particle moving in some potential V of r. The way you derive the probability current is to multiply this equation by psi star, the complex conjugate of psi, and the complex conjugate equation which is minus IH cross delta psi star of r and t. This is equal to, and notice it is h cross squared over 2m, and you complex conjugate it, this thing becomes psi star here. So del squared psi star, the complex conjugate, plus the same potential because it is a real function, no complex conjugation there, times psi star on this side. So all you have to do is to multiply this equation by psi star and this equation by psi and subtract one from the other, and if you did that you end up with IH cross delta over delta t psi star delta psi over delta t plus psi delta psi star over delta t. This is just delta over delta t mod psi squared this side, and that is equal to minus h cross squared over 2m times psi star del squared psi minus psi del squared psi star, and this term, the potential term, cancels out on both sides when you subtract. So independent of the potential, no matter what the potential is, this equation is true on this side. So just make sure the signs are right. There was a minus h cross squared over 2m psi star this thing, and then this became a plus sign, so I compensated with a minus sign there. Okay. But this guy here is like the divergence of a current, because notice that if you took the divergence of psi star grad psi minus psi grad psi star, this is the divergence of a scalar times a vector, and you know there is a formula for the divergence of u times v, where u is a scalar and v is a vector. It is grad u dot v plus u divergence of V. So that gives you, this is equal to del psi star dotted with del psi plus psi star. Del dot del is del squared on psi, and then minus grad psi dot grad psi star minus psi del squared psi star, and of course the cross term cancels out. Therefore you could write this as equal to minus h cross squared over 2m divergence of psi star grad psi minus psi grad psi star this side. Okay. And let us cancel out and divide by I h cross, so move this out and then I put an I here and this becomes h cross. So indeed you have an equation of this kind with rho equal to mod psi squared. The charge density in this case is just the probability density plus the current is this quantity, so J equal to h cross over 2mi psi star grad psi minus psi grad psi star, and this quantity is called the probability current density. It is a real quantity because it is this complex number minus its complex conjugate divided by I, 2i. So it is in fact a real quantity, it is the imaginary part of psi star grad psi essentially. And so this looks exactly like a continuity equation, and just as the probability density had a bilinear psi and psi star, it involved both of these guys. Similarly the current density also involves both these quantities here. Now if you have a charged quantum mechanical particle moving, then if you multiply this by the charge of the particle, you could in fact associate it with the real physical charge density and the physical current density, the electric current density here. So this is something we keep in the back of our minds, that for a quantum mechanical particle, we are going to look at the behavior of a charged particle in electromagnetic fields. This quantity here multiplied by E will become the current density, the actual current density. But right now let us look at this expression itself. It is Hermitian, or it is real in this case, in this representation, and it obeys a continuity equation here. So although the Schrodinger equation was a linear equation in psi, notice that these quantities are not linear, they are bilinear. They involve combinations of psi as well as psi star. When we do a little bit of scattering, I am going to come back to this quantity here and talk about the meaning of this quantity. You will see what how this can be related directly to a physical quantity in scattering processes. Okay. Now the other point I wanted to mention, which had been left out inadvertently, was the spread of a wave packet. So let me spend some time on that, and it will also give us some practice with regard to the Heisenberg picture and the Schrodinger picture. Okay. In the problem set that I have sent you, I have mentioned something called Ehrenfest theorem, and I have also mentioned something about how a Gaussian wave packet spreads. Now let us look at this in the simplest instance and see what happens in one dimension. So I have a free particle or a particle in a potential to start with, it is propagating, let us say in the x direction, and now under some potential possibly, and now the question is, if I prepare an initial state of this particle such that it is localized around some point x naught, so a little wave packet peaked at x naught and let go, what happens to it? This thing here would propagate under the Schrodinger equation, and you could ask the question, what happens to the shape of this wave packet as time goes along, and let us look at what a general result is. So I am going to look at a state psi of t of a particle, and I am going to ask what happens to the mean value of the position or the mean square value of the position and so on. Now you know that if you have a Gaussian wave packet, the peak position would actually give you the value of the mean, and if the peak, if it spreads out or if it contracts, you know that the wave packet is either dispersing or it is getting more tight. So let us ask what this quantity is, x squared, the square of the position psi of t. X itself is trivial to compute, so let us look at x squared and see what happens. And the Hamiltonian of this particle is p squared over 2m plus some potential in general. Later, a little later, we will look at a free particle. Okay. So given that Hamiltonian, I would like to ask what is this guy, what is this going to be, and of course this is what I call x squared as a function of t. And like I pointed out, you can compute this either in the Schrodinger picture or in the Heisenberg picture. In the former case, I would regard the time dependence as coming from the wave function. In the latter case, I would say the operator itself depends on time. Well, let us see what this quantity does. So let us do it, and I am going to do both, one or the other, depending on what how I feel, what I feel like. So d over dt x squared equal to differentiate, what happens? Well, it comes from, in the Schrodinger picture, it would come from differentiating this and this. So this is equal to d over dt psi acting on x squared psi on this side. So I have this guy here to compute plus, assuming I have normalized it, it is psi x squared d psi over d on this side. Okay. And I use the Schrodinger equation for these two quantities. So I know the Schrodinger equation is IH cross d psi over dt equal to h psi, and the conjugate, the adjoint equation here is minus IH cross d over dt of the bra vector psi equal to the bra vector psi, the Hermitian conjugate of h, but h is a Hermitian operator, so there is no dagger here, it remains as it is, and I plug those in. So this is equal to psi h x squared psi, but that was with a minus IH cross, so let us put the minus IH cross downstairs in this fashion, plus psi x squared h psi, and there is an IH cross here. Okay. So this is equal to 1 over IH cross expectation psi Poisson commutator of x squared with h psi, because you got a plus x squared h and minus hx squared, and you have to find the expectation value of this commutator here. What is this commutator itself? Let us find x squared h. This is equal to 1 over 2m commutator of x squared with p squared, and then x squared with v of x, and what is that? It is 0, because there is the x operator and a function of the x operator on both of these terms, and it commutes with itself. So that term is 0, and I need to find this, and this is equal to 1 over 2m times x with p squared plus x with p squared x, because that is the rule for finding these products, Poisson commutators of products. So you got to be careful with the order here, because x and p do not commute with each other. So one fact, x squared is x times x, and the first factor I write here, the second factor I write there, I pull it out, plus, that is it. This is equal to 1 over 2m, and x with p squared, I could write this as xp x with p plus x with p. So I do the same thing again, x with p squared, I write it twice in this fashion, plus p times x with p x. Please notice, if I write this as p times p, one factor p comes out, and then it is x with p with an x, and the second time around it is x with p and then a p x. So you have to be very careful with the order of these terms, otherwise you are completely wrong. And that is not difficult to find out now. So it is 1 over 2m, x with p is IH cross times the unit operator throughout. So I pull that IH cross out, IH cross, and then I have an xp and then again an xp because this guy turned out to be the unit operator plus px plus px. So just a factor of 2 and then xp plus px plus, if it were minus of course it would just become the unit operator, but a plus sign, anti-commutator of x with p. So this is equal to IH cross over m xp plus px, and let us put that in here. So this guy here becomes equal to, in general the 1 over IH cross goes away and you are left with 1 over m expectation value of the anti-commutator xp plus px. That is a general result, and it is typical of these problems because you see it is not as if this is going to reduce to something simple. The expectation value of this guy reduces to something, this is the second moment of x, it involves an antisymmetric symmetric combination of x and p here, and now you say okay, this too is a physical observable, xp is certainly a physical observable, xp plus px is certainly a Hermitian combination. So I now try to find its equation of motion, d over dt of this, and then you will discover pretty soon that this series never truncates, it just keeps going because you will get more and more multiple commutators, and even though you started with x commutator p is just the unit operator, when you start taking all the moments of x and p in general it is an infinite hierarchy of equations, does not close in general. So even in the simplest of problems you end up with an infinite hierarchy of these things. Not surprising because after all you can say about this system is in terms of its state vector or probability distribution, and you know that the probability distribution in general is specified by an infinite number of moments, and that is exactly what will happen here. You need to know the first moment of x, the second moment, the third moment and so on, but because of the non-commutativity you have other problems. You need to know the same thing for p, and then you need to know this for the expectation values of various combinations of x and p, xp plus px, xp squared x, xp, xp and so on. You will have an infinite hierarchy. So this is our first result, that the d over dt of this is simply turned out to be just this quantity here. Look at what happens if you find the second derivative of it. So let us do that. Now of course you have to sit down and write what this expectation value is, and it is not going to be trivial because you have this xp plus a px. Well, let us simplify this a little bit and see what happens. So 1 over m xp plus px, this is expectation value in any state of the system psi. Let us do it in the position basis and see what happens. So in the position basis, I mean in the abstract sense, this is equal to 1 over m psi of t x operator p operator plus p operator x operator on psi of t, but you could also write this in the position basis. I will write everything in terms of the wave function psi of x comma t, and then this becomes integral from minus infinity to infinity dx psi star of x comma t. That is what this stands for. The bra here is replaced by psi star if you like in this space of square integrable functions times x times the p operator, but the p operator is minus IH cross d over dx, or let us put partial derivatives because you got t dependence as well, and this acts on psi of x comma t. That is the meaning of this p in the position basis. Notice it sits here as a derivative operator, acts on whatever is on the right hand side to its right, plus delta over delta x, x psi x times psi of x comma t product. And I have no choice, this p is to the left of this x operator, So it acts on everything on its right hand side, and there is a d over dx gradient with respect to x of everything to its right on this side. Well, what does that become? That becomes minus I h cross over m integral minus infinity to infinity dx psi star of x d. So let's ignore the arguments for a moment. Psi star x delta psi over delta x is the first term, and then in the second term here let us integrate by parts. So I have to do an integral psi star delta over delta x x psi. I would like to throw the derivative on the psi star now, and what does that become? Minus, when I integrate by parts, minus delta psi star over delta x times x psi, because if I integrate this term by parts you have an integral and then the surface term and then another term which is just the derivative acting on this guy with a minus sign. And what did I leave out? I left out minus I h cross over m psi star of x comma t x psi of x comma t at x equal to minus infinity plus infinity. That was the surface term I got by integrating this term. Now if these wave functions are square integrable and you are in L2 and the mean value of x is finite and so on and so forth, then this term vanishes at plus minus infinity sufficiently rapidly, because the wave function is supposed to vanish at plus minus infinity sufficiently rapidly, and you are left with just this term. But there is nothing to stop you from pulling the x out in here, because that is not getting differentiated anyway in this fashion, and then you pull the I down, so this becomes h cross IMI, which is equal to, but you recognize the probability current was h cross over 2 mi psi star grad psi minus psi grad psi star. So you could in fact write this as 2 over 2 twice integral minus infinity to infinity dx x j of x comma t. But j was the probability current density. So you see these are related, this current density is related to measurables, because when you multiply it by x and you integrate, you in fact get the time derivative of the mean square, the expectation value of the square of the position of the particle is directly connected to this current density. Now let us try to evaluate this by taking its second derivative and see what happens, and let us do it in the Heisenberg picture just for the heck of it. We worked it out in the position representation, in the Schrodinger picture. Let us see what happens in the Heisenberg picture. So I have, let us write the result down and then I evaluate it. So we have d over dt of x squared, let us forget the t, is understood. This is 1 over m expectation xp plus px. So d2 over dt2 of x squared, the second derivative of this is 1 over m, and now let us work in the Heisenberg picture. So I do d over dt of this guy here, but d over dt of any operator is the commutator of this operator with the Hamiltonian divided by IH cross. That is the Heisenberg equation of motion. So let us write this as 1 over mi h cross times the expectation value of the commutator of xp plus px with the Hamiltonian, which is p squared over 2m plus v of x. In general you can't go very far, I mean, because now you need the commutator of p with v of x, and that will be a big mess, it will be generally v prime of x and so on. But look at what happens to a free particle. So free particle, v of x equal to 0, the Hamiltonian is just p squared over 2m, and then you expect that in the case of a free particle the Hamiltonian commutes with the momentum operator, and therefore you expect that momentum eigenstates are also position eigenstates, are also energy eigenstates of the Hamiltonian. Let us see what if that is borne out. So for a free particle, since V of x is 0, we can compute this quantity xp plus px with p squared over 2m, and so it says d2 over dt2 x squared equal to, on this side 1 over mi h cross, commutator of xp with p squared over 2m. So let us pull out another m, 2m, so it is 1 over 2 m squared I h cross, expectation value of x with p squared, and that is all you need. So x with p squared with a p outside, because p with p squared of course commutes, and there is no v of x, so this term does not contribute here, plus, and that is all this term is, plus p times again x with p squared expectation. What is x with p squared? 2 I h cross times the derivative of p squared with respect to p, which is 2p, right. So it is twice I h cross p, and the twice I h cross cancels, and this gives you 2 I h cross cancels, so it gives you a p squared plus a p squared, so it is 2 over m squared p squared. Okay. So actually you have a very simple result now. The second derivative for a free particle, the second derivative of the square of the position, that operator is just 2 over times the expectation value of p squared, but the expectation value of p squared over 2m is just the energy for a free particle. It is a momentum eigenstate, so let us suppose that it is in a momentum eigenstate with some value of p. So let some value of p, or maybe a wave packet. In either case this quantity p squared is independent of time, because this quantity commutes with the Hamiltonian, and therefore its expectation value is independent of time. It is a constant, you have to prescribe to me what it is at t equal to 0. This is a constant of the motion. P squared is independent of time, because this is just a function of the Hamiltonian itself, okay. And no quantity which depends on the Hamiltonian without explicit t dependence, its expectation value is independent of time. It depends on what the initial momentum spread was, we do not care, but it is some number. So that immediately says therefore d over dt of x squared is equal to twice over m squared p squared multiplied by time. I am just integrating with respect to time, plus d over dt of x squared evaluated at t equal to 0. That is a constant of integration. These expectation values are real numbers, they are functions of time, that is it. They are not operators or anything like that, they are not wave functions, they are not operators, they are just numbers, and in this case in general these would be some complex numbers, but these are Hermitian operators and the expectation values are some real numbers, and they are functions of time. So we get our first result which says the square of the position, its average value, the second moment of the position, its time derivative is related to time by a linear function plus a constant of this kind, and we can integrate it once again. So it says x squared as a function of time is equal to, did I integrate correctly? I just integrate with respect to time, plus let us call this guy something. This is the value of the spread in the wave packet, the second moment of the position at t equal to 0. So let us call this thing some k0. it is a number, it is some constant, plus k0 t plus x squared at t equal to 0. Now notice that for a free particle classically, if it is moving at constant speed, its position as a function of time is linear in time, and the square of its position is a quadratic function of time, and in general is of the form at squared plus bt plus c. You are almost there, except these are for expectation values, and it looks like this, and it is trivial to ask what is x itself. So let us do d over dt of x average itself for a free particle. Once again, this is completely trivial. This is equal to 1 over IH cross expectation value of x with the Hamiltonian. Once again I use the Heisenberg equation of motion, and that is equal to 1 over IH cross, and then there is a 2m, the Hamiltonian is p squared over 2m, so it is the expectation value of x with p squared, because there is no potential, and even if there were, this would cancel out in this particular case. This is equal to 1 over 2m IH cross, and x with p squared is 2 IH cross expectation value of p. And the 2 IH cross cancels, and it gives you a result which you expect, it is p over m. So the peak position, if you start with a wave packet which is centered at the mean value, a symmetric distribution about the mean, that works expectation value of x as a function of t is therefore equal to this quantity, that is again a constant independent of time because it commutes with the Hamiltonian, pt over m, plus whatever was this guy at t equal to 0. What does this remind you of? This is how a classical particle would move. If you tell me its speed, it's p over m, and the speed is constant, momentum is conserved in the problem, then its position at time t is the position at time 0 plus speed multiplied by time, or velocity multiplied by time, and now the same equation is being obeyed by expectation values in general, no assumption made here. Even for a non-free particle this is true, because this quantity here would have an extra v of x, but x would commute with that v of x. So it says that this average, the expectation value of this physical quantity, behaves like a classical particle. But of course once you have to be careful here, this is true for a free particle because I assumed this quantity was independent of time, and that is only true if you do not have a potential. So while this first step goes through, this commutator is correct, this quantity you cannot integrate now to say this is equal to pt unless you have a free particle. So we are only working with a free particle all the way through, so all this is for a free particle. And incidentally this was also true for a free particle, as we saw a little earlier. So quantum mechanical expectation values obey classical equations of motion, that is the content of the Ehrenfest theorem. This is not always true. It is not true, for instance, if the classical dynamics is chaotic, then this theorem breaks down, and that took a while to realize, but these very simple cases where there are no other problems like ordering problems and so on, this theorem is true, and this was first pointed out by Ehrenfest, and I have written a little bit about it in the problem set. But now you could ask, what does the uncertainty do? What does the wave packet do? And you will see immediately that I start off with a wave packet at t equal to 0. Suppose along the x you had a wave packet prepared like this. This was my mod psi squared, the initial probability density. So mod psi of x0 whole squared looked like this. So there was some initial position x0 and there was some width here which is related to delta x, which is equal to the x minus average x whole squared to the power half at t equal to 0. That was my initial uncertainty in the position, and the initial wave packet was centered about some x0 say. Okay. Now I let it go, and let us suppose the momentum is in the forward direction, expectation p is in the forward direction. Then you are guaranteed that the expectation value of x will change with time linearly in this fashion. This number was x0 out there for that symmetric distribution, and the mean square would increase with time also like t squared here. Okay. And now the question is, what does the uncertainty do? Delta x itself too. So what you have to compute is expectation value of x minus x average whole squared as a function of t, but that is the same as x squared as a function of t minus x average as a function of t whole squared. So all you have to do is to square this guy and subtract from this fellow. What happens? What would the uncertainty do? Would it increase with time? In general this does not cancel. Notice that this does not cancel at all. This is guaranteed to be a positive number and will increase with time. There is dispersion. This wave packet actually increases with time. So I leave you to find out what the increase is, what it's very much like the solution of the diffusion equation in this case, because the equation is more or less the same for a free particle. And this dispersion occurs because you can regard this pulse as being made up of different Fourier components, and they would have different, the phase velocity and the group velocity would not be the same, because for a free particle remember that the energy momentum relationship is quadratic. E is p squared over 2m, or h is p squared over 2m. So if I write the energy as h cross omega, the angular frequency omega in the wave picture, and the momentum as h cross k, where k is the wave number, then I get a relation which says omega of k equal to, this is h cross omega is h cross squared, so it becomes h cross k squared over 2m. So there is a quadratic relationship, and this immediately means that d omega over dk is not equal to omega over k. Therefore the group velocity is not equal to the wave velocity or the phase velocity, and different wave numbers would propagate with different speeds. Therefore you get a dispersion immediately, and that is being reflected here in saying that if I start with an initial wave packet, it is going to spread as a function of time even if there is no potential, because the relationship between the energy and the momentum is not a linear one, or the wave frequency and the wave number is not a linear relation. Give me an example of dispersionless motion. Is there something which says no dispersion? Some physical wave motion where there is no dispersion, some physical situation where you do not have dispersion in wave motion. Yeah? Well, I mean, if I put light through a medium, it certainly disperses, right? Put it through a prism or water or air even, it will disperse, because all these media, after all, passage of light through a medium involves the interaction of photons with the atoms of this medium, and there is no guarantee that this interaction is the same for all frequencies, certainly not true. So this is what is responsible for dispersion. You know, the refractive index depends on the wavelength. But when does light not suffer any dispersion? In a vacuum, in free space, it does not suffer any dispersion at all. In free space, you know that epsilon is equal to h nu, right? I mean We can start the other way. So we can start by saying nu times lambda equal to c, where nu is the frequency and lambda is the wavelength. This is equal to the speed of light in vacuum. Well, what is nu? This is equal to omega over 2 pi, that is the angular frequency, right? And what is lambda in terms of the wave number? 2 pi over k or whatever it is, right? So there is a 2 pi over k equal to c, or omega equal to c. Actually, if you have propagation in different directions, this is c modulus k, the vector, wave vector k, magnitude of it. So this implies that d omega by dk equal to c omega over k, and you have no dispersion. So electromagnetic wave of all wavelengths, it travels with exactly the same speed, the fundamental speed, in a vacuum, and the reason is, of course, that the relationship is linear in this case. Similarly, if you look at sound, omega is equal to ck, where c is the speed of sound. If you look at sound propagating in a solid, then for acoustic phonons, what are called acoustic phonons, omega is still equal to ck. But in a crystal, this is not what happens. If you plot the wave, the frequency versus wave number for acoustic phonons inside a crystal, because in a crystal sound is propagated by all these guys moving cooperatively in a crystal, then while the relation starts linearly, it tapers off to what is called the edge, the Brillouin zone edge, and in this region you have what are called acoustic phonons. Okay. If this crystal has anisotropy, in other words, in the different directions, along the principal directions, the crystal structure is different, or the arrangement, the lattice constant is different or something. You have a simple cubic crystal, all three directions are exactly the same lattice constant. Then you have a tetragonal crystal, which is still a member of the, the three principal axes are still perpendicular to each other, but two of them have the same size, same length, A, and this guy is something else, C say. Then this sound propagation in the three directions splits up, and you have two branches, one of which is doubly degenerate and the other fellow splits off in this fashion. The slopes are different, so the speed of sound is different in the two directions. And if you have an orthorhombic system where you have three lattice constants A, B, C in three perpendicular directions, then you really would have three modes, three branches. You have one like that, another like that, and the third one like this, and the propagation will be very different, but they are all linear to start with, at least very close to this edge. What would happen if the photon had a mass? After all, that is what electromagnetic waves are, when you quantize them you get photons, and this relation here is equivalent to saying that the energy of a photon is linearly dependent on its momentum, because all you have to use is Einstein-de Broglie relation. Epsilon is h nu, so nu is epsilon over h, Planck's constant, and lambda is h over p, and that is equal to c, or epsilon equal to cp. That is the linear relation between the energy of a photon and its magnitude of its momentum, and you have no dispersion at all. Suppose the photon had a rest mass, it does not as far as our theories tell us, but suppose it had a rest mass, what would happen? What would happen to this relation? It would go over into the relation between the energy and the momentum for a relativistic particle, and what is that? Yeah, what would that relation be? Instead of this you have a different relation, and that is not a linear relation, right? That is equal to epsilon squared is c squared p squared plus m squared c4, where m is the rest mass of the particle. That is the correct relativistic relation between the energy and momentum of a relativistic particle of rest mass m. And the moment you have this and I put this is equal to h cross omega, so you got h cross squared omega squared is c squared and p is h cross k, so h cross squared k squared plus m squared c4. Now you got a different kettle of fish altogether, because you realize that if okay, let us divide by this guy and omega is this fellow here. This is no longer a linear relation, and therefore d omega over dk is not the same as omega over k, which means you would be able to detect a non-zero m by looking at an event from very far away going through interstellar space, essentially vacuum, and finding out if there is a time delay between the arrival of photons of one wavelength and another wavelength, and you can actually compute what that time delay is. And there are these very intense gamma ray bursts which happen in the universe very far away, and you have to now make many corrections. You have to ask, is it going through interstellar gas, is it getting dispersed on the way because of the medium and so on, but by and large most of space is empty. You look at a very distant intense gamma ray burst, and there are many of them have happened. A notable one happened in 1998, for example. They are called giant gamma ray bursts, GRBs, and then you wait for the gamma rays to come, and then you wait for the optical photons to come, and then you wait for the radio photons to come, and so on, and sometimes there could be a delay of days between them, sometimes seconds, depends on the wavelength. And by measuring the time delay between say optical and radio waves from the same event, gamma would come in practically instantaneously, you can compute what this m is, how big this m could possibly be. By the way, what is the significance of this quantity? What is the significance of mc? You notice that mc is a typical momentum, it is called the Compton momentum, and of course h over mc is the Compton wavelength. Of a particle, and it is like the size of a particle. If at all you can attribute a size to these quantum objects, h over mc is a good candidate. It is like the extent of this particle. Now what happens if m is 0? It is infinite. So a photon is completely delocalized. A single monochromatic wave is delocalized, it extends from minus infinity to plus infinity. On the other hand, you get it more and more compact, it is almost 0 and then there is a big pulse here and then 0, you get localized more and more. It is clear that in wavelength you are really spreading it more and more. The more you localize in the position, the more you are spreading in momentum or wave number. So this is used in fact to put upper bounds on this m. It turns out that the best bounds we have are of the order of m is certainly less than, you can never say something is 0 in physics, that is very clear. All our theories require that the photon have exact 0 rest mass, but then of course experimentally you can never say something is 0, you can say it is less than this or so, and it turns out the best bounds on the photon, most reliable ones, would correspond to m of the order of less than 10 to the minus 50 kilograms or 52 kilograms or something like that. There are estimates which come from galactic magnetic fields of the order of 10 to the minus 60 and more kilograms, but they are not as reliable. What is the other consequence of the photon not having 0 rest mass? You have to go back and re-examine Maxwell's equations, and they are written down for 0 rest mass, because you had the wave, if you recall, you had the wave operator acting on the electric and magnetic fields. In free space you had electromagnetic radiation in which the electric and magnetic fields obeyed the wave equation, and that gets modified by precisely this term here. And why? Because this is again quantum, it is very simple to see this. If I write this equation quantum mechanically for a particle, and I use the old Einstein-de Broglie way of going to quantum mechanics, which is really all that there is to it, then this epsilon is, so let us bring this to this guy, minus, let us put a minus here, and put this equal to 0, and now I say no, this is like an eigenvalue equation, it's a relation between eigenvalues. So really this comes from the Hamiltonian, and the Hamiltonian acting on a wave function is IH delta over delta t acting on the wave function. So this is minus h cross squared d2 over dt2 acting on the wave function psi if you like, minus c squared, and what is this guy? P in the position basis is minus IH cross gradient acting on the wave function. So c squared minus IH cross squared del squared acting on the wave function minus m squared c4 acting on the wave function, this whole thing acting on a wave function in position space psi of r comma t equal to 0 if the particle is described by a wave function, a single component wave function like psi of r comma t. Can we simplify this a little bit? Well, we can certainly get rid of some minus signs. This gives you a minus, so this becomes a plus h cross squared, and this is a minus, so let us remove this minus sign, make this a minus and make that a plus, and let us divide by h cross squared. And while we are at it, let us divide by 1 over c squared. So 1 over c squared minus del squared plus m squared c squared over h cross squared acting on psi of r comma t equal to 0. If you did not have this term, then it is just the wave equation, which is what the electric and magnetic fields and so on would obey. And in fact in the case of the electromagnetic field, you know that you can replace the electric field and the magnetic field B by a scalar potential and a vector potential. So you can replace this by a scalar potential A and a vector potential, scalar potential phi and a vector potential A. Together these form the components of a 4-dimensional vector in 4 space, and this quantity here is the 4-dimensional analog of the Laplacian operator in 3 dimensions with the time metric taken care of, namely that it is c squared t squared minus r squared, which is the square of the interval in relativity. This has a name, it is the D'Alembertian or the box operator, box, plus m squared c squared over h cross squared on psi of r comma t equal to 0 would be the equation for a particle which is described by a single scalar wave function psi of r comma t. This equation is called the Klein-Gordon equation. So although I am not supposed to do relativistic quantum mechanics in this course, no harm in knowing that this is the Klein-Gordon equation. It replaces the Schrödinger equation in relativistic quantum mechanics. It is an interesting historical sidelight that Schrödinger actually wrote this equation down first, even before he wrote down the original equation for the non-relativistic case. He wrote this down first and then gave it up as unphysical, and the reason he gave it up is because if you calculate from this quantity the probability density in this problem, then instead of the probability density being mod psi squared, which is the probabilistic interpretation of quantum mechanics, if you compute from this quantity the probability density from this equation, it turns out to be psi star delta psi over delta t minus delta psi star delta t psi. That turns out to be the probability density rho. Then he was puzzled and he thought this was wrong, because that quantity on the right hand side can take either sign divided by I, so that is real and all that, but it can take either sign, and he said how can a probability density be negative, and so he gave it up. And then Klein and Gordon wrote this down and they got the correct equation. but actually the Schrodinger wrote this down first, and then once he wrote the non-relativistic equation mod psi squared was the probability density, everything came out consistently and there was no difficulty, but in fact he was not wrong. It turns out that this equation is applicable to charged particles, and then if you multiply it by E, it is the charge density, and there is nothing which says that charge densities have to be positive or negative, it could be negative, could be positive. So he missed out on discovering relativistic quantum mechanics, although he discovered it first, he wrote it down simply because of this conceptual problem at that stage. But in any case this equation goes by the name of the Klein-Gordon equation here. Now coming to the photon, you have not one wave function but you have 4 quantities, you have this plus this, and together you know that phi over C A is equal to the 4 vector potential A mu, and Maxwell's equations in their original form is represented by del A mu equal to 0, or the current density on the right hand side if you have sources. That is what a free photon does, but now you replace it by this plus that acting on A mu as a function of R and T equal to 0. So Maxwell's equation, the D'Alembert on A mu equal to 0 is replaced by this wave equation. You must now regard this as the wave function of the photon, if you like, it is really the fields, and this equation has a name, it is called Proca's equation. So even the basic Schrodinger equation for the photon, which is really relativistic always and therefore it is really a version of the Klein-Gordon equation, in this case is something else, it is this equation once you go to a massive photon. Now please recall that if you go to electrostatics and this term goes away and you work in what is called the appropriate gauge, the Coulomb gauge, then you know that this leads in electrostatics to del squared phi equal to rho over epsilon naught or whatever it is, and if you got a single charge at the origin then this is equal to a delta function at R over epsilon naught with a minus sign multiplied by the charge density. So this is equal to minus E times sky. What is the solution? It is the electrostatic potential due to a point charge at the origin, and that will tell you that it is phi equal to E over 4 pi epsilon naught R, that is this 1 over R, Coulomb potential. The moment you have this extra term in this static limit, this gets modified, this potential gets modified, and please notice that the scalar potential going like 1 over R leads to the inverse square law of force, it leads to the fact that Gauss's law in electrostatics is valid. You put a charge inside some region and the flux over a surface of the electric field around the surface is equal to the charge divided by epsilon naught, etc. All those things go out of the window the moment you have a correction to the photon mass. This guy gets modified and instead goes like e to the power minus mu r over r, and this potential is not a 1 over r potential, it dies down at far long distances much greater than that, and this mu must have the inverse dimensions of a length, it is the inverse of the Compton wavelength. So this mu equal to mc over h, precisely equal to that. Therefore the inverse square law is not valid, the Cavendish experiment to test the inverse square law will undergo a modification, Gauss's law in electrostatics will undergo a modification, and you can actually test and find out if the inverse square law is valid or not and get a limit on the photon mass. This is our best experiment yet, and it shows that the photon mass, if it exists, is certainly less than 10 to the minus 50 kilograms, and constantly people try to improve it. So you see there is a very intricate chain of argument but not very difficult to understand, which takes you to these things. Now in this course I am also going to discuss not the electromagnetic field, but I am going to talk about spin, and then we will make some connection between why you get more than one component here and what the role of the spin is in making sure that you do not have a scalar wave function here. So that is one of the topics we will look at very shortly. But coming back to what we did about wave packets, I thought you should appreciate clearly the fact that owing to the fact that non-linear relationship between energy and momentum, even for a free non-relativistic particle, any initial state, any initial wave packet disperses in space.